Well, hello. What we're going to do tonight is we are going to compare, or we are going to use R to do our Benford's law calculations. If you think back to the last video, the one that was called Benford's law part 2 Excel, in that we took our data, which would have been these numbers here, the census data, we put it into the spreadsheet, we copied the formulas all the way down, and we ended up with a table. This would be our first digit table over here. And from this table, we did a first digit graph, which was our Benford analysis. In this case, the fit is reasonably good. At least it is visually good. What we are going to want to do is we are going to want to get R to do as much of this as possible. And once we've got as much of this done as possible, we can do the graph. We can actually do it in R, or we can use Excel. So let's go to R Studio. We have 4 components over here. This is the editor, and this is where we are basically going to write the code that we want R to execute. Over here, we are going to, R will read, evaluate, and print for us. Hopefully it doesn't print error messages, it'll print part of the output. What we care about here in the environment are the variables and the data sets that we have created along the way, and I like to use this to at least have a look at my output and see whether it is reasonable. The bottom part here could simply be called miscellaneous, and the ones that we care about most are files and unfortunately sometimes help. So the good news is, in the description to the video, I have done quite a lot of the hard work, and it'll all be in this Word document called Benford's Law in R. We are going to use R Studio, and what we're going to want to do is replicate as much as possible of this table, and once we have this table, we can move on to the graph. So, what do we have here? We have the first digits, 1 through 9. Every non-zero number is going to have a first digit, 1 through 9. 0 can never be a first digit. We will take the first significant digit. So in something like 0.02, that first digit will be a 2. It will count how many 1s we have, how many 2s we have, how many 3s we have, all the way up to how many 9s we have. We will get the actual proportion, which is the count divided by the number of records. We'll have the Benford's law proportion, 30.1, 17.6, 12.5%. We get the difference between the two. The bigger the difference, the worse that graph looks. We'll get the absolute value of the difference, which means we don't really mind whether the difference is going in that direction or going in that direction. And we'll get a mean absolute deviation, which is the average of these absolute differences. And this will be our big clue as to how well our data set conforms. The Z statistic over here will tell us whether our difference is statistically significant when the number is higher than 1.96. That means the difference, in this case for the 5, is statistically significant at the 5% level. When it is greater than 2.57, it means it's significant at the 1% level. The Z statistic has this formula here, which will require just a little bit of fancy footwork in R, especially since this term is only used under certain conditions, so we have to do something like if something, then else, otherwise. So let's go. This is our R code. We'll do it slowly. I'm going to prepare the first digit table, and the first thing I'm going to enter, well, the first 2 things in this case, we'll go here, we'll move over to R Studio, we'll put the code in, and in fact, I don't need to highlight the comment there. We'll highlight this and we'll do run, and very nice. We now have a vector, 1 through 9. So far, so good. We have entered the counts manually. So this is how we have to start. Let's just put the counts in manually, get the table, and we get to a point where we can get R to do the counts for us, and we'll get there not soon. So These are the counts. I have my first two columns. Let's go on. When I calculate the actual proportion, I need the number of records. And we'll highlight this here. And we'll run. And now, there were 3,142 counties. And now it can calculate the actual proportion, which is the count, 953, divided by the number of records, n. And so I have all my actual proportions. They're over there. You can compare them to the table. They're pretty good. Benford's law, pretty easy. It's a formula. And we'll call this Benford prop. So we'll go back to R. And we'll go in here. We'll do a paste. And now I'm going to run just this line. The cursor is there already. And my Benford proportions are there. 30.1, 17.6, 12.5%. This is going quite fast. This will slow down in a while. Now, to get my mean absolute deviation, I need to do 3 steps. And here we go. The first of these, I need to get the difference, which is the actual proportion minus the Benford proportion. I need to get the absolute value of the difference, which is abs, the absolute function there, absolute value of the difference. By the way, this thing here means it's our assignment. It means absolute difference is, or you can say absolute difference equals. That's what it is. Abs diff is that over there. And let's see whether we get our mean absolute deviation already. I need to run, what do I have? I have Ben prop, I have actual prop. I need these 3 to run. So we'll do run, and I get the difference, I get the absolute difference, and I get the mean absolute difference, 0044. The nice thing is, if we go here and we scroll up, the mean absolute deviation is, well, it's got 0045 here. I'm hoping that's just a little bit of rounding somewhere along the line. Get back to R. 004, actually, if you round this, it'll go 0040. So no difference, just a little rounding. Now, this is a little bit of hard work here. This is the Z statistic. It is the absolute value of the actual proportion minus the expected proportion. That's not too hard. We have it here. Minus 1 over 2n. We have the count. Here it is. We have n, so 1 over 2n is no biggie either. This is the expected proportion. This is Benford's law. This might look a little messy with the square root sign and this over here, but not too difficult to code, as we'll see in a moment. This is the problem. This is a continuity correction term, and it is only used when it is smaller than the first term. So if I go this minus this, I need to get a positive number. If I get a negative number, it means this was bigger than this. So I only subtract this if this number is smaller than that. And unfortunately, now things get a little tricky, mainly because we're using vectors. I need to calculate the one minus the other. So far, so good. And I only need to do this part if this part is smaller than that part. I actually need to write a function here. This is called correct function, and it is a function of the absolute difference and this second term over here. What this says is, if I subtract and the number is greater than 0, which means it's good, then do the subtract, then do it. Otherwise, if it's less than 0, if it's less than 0, then just give me the absolute difference. Otherwise, give me both terms. We've got j over here, and we're using this for j in 1. This is a little tricky, but you know, you don't even have to understand how it works. Trust me, it's going to get it right, and it's going to get it right for us. And we have all sorts of braces over here. And then I'm going to get two things. I'm going to get the top, which is the correct value of the top. I'm going to get the bottom. I don't want to call it numerator and denominator. I'll calculate the bottom separately. And then to get the z-stat, I will go the top divided by the square root of the bottom. Well, I'm getting the bottom without taking the square root here over here, and I'm taking the square root over here. You know, it's a bit complicated, but all I have to do is really go in here and do this. Is everything off the mean absolute deviation. We'll do copy. We'll go back. We'll do paste. And now we've got to grab everything after mean absolute deviation and run. And let's see what I have. My output is a z-score 0.259, 1.884. And if we go back here, 0.259, 1.884, it calculated it correctly. Use and enjoy. However, what I have in R now is separate vectors or separate columns. I need to combine them. I need to combine them so that I can get something that looks like, sorry to make you dizzy, like this. And what I really would struggle to do in R is to put the mean absolute deviation at the bottom over here. So what I'm going to do is I'm going to add another column here called mean absolute deviation, and it'll give me 9 mean absolute deviations. They'll all be correct and they'll all be the same. So I'm going to call my matrix Ben test is, and over here I use C bind, which is column bind. Chunk them together as if each one was a column. And in fact, this is a single number. It'll make 9 of them. So here we go, Ben test. And just be careful at this stage of your work. R is case sensitive. So each one of these has to be typed exactly as it is. Otherwise, it'll come back to you and say variable not found. And we don't like little messages like that. Control D is to paste. Here it is. So I'm doing the C bind. This all fitted on one row. Thank goodness. Other things would be 2. And so now we'll go run. And it's got, it looks like it's very busy over there. And this is actually good. So let me actually see what we've got. Ben test. And in fact, when I type it like this in R, Control V, it's just telling me, and we'll do run, it'll give it to me now. Isn't that beautiful? First digit, the counts, actual proportion, Benford proportion, difference, absolute difference, z-score, mean absolute deviation. I have in fact, I'm happy to say, I have replicated this. And if I've replicated this, you can actually go into my Negrini cycle. You can put your own numbers here. You don't even have to do the graph. You can put your own numbers here, and the first digit graph will automatically populate based on whatever you put in this table. So we're almost good to go. Now we're going to add a few nice finishing touches here. I've got Ben test, so I can see that I have the, I'm going to set my working directory, and I'm going to write the file as a CSV file. So we'll go copy, Control V. RStudio is neat. It can do almost anything. We're going to run. Set working directory. No, don't tell me that you're doing this to me. Let's try this one at a time. I'm going to just pause. Well, hello, I'm back, and what I did was I went back and I said get working directory, which wasn't this over here. And then what I did was set working directory, which is on my C drive, and it's the folder called R, and then write CSV. And in fact, we're writing this output out as a CSV file. And it took a little bit of work to figure out what I might have done wrong, but I might simply have tried to execute these two lines together. And if I say get working directory now, it definitely sees it's CR. I'm going to execute this line right over here, and we'll do run. And now it has written out that table as a file, Benford R CSV. If I go to this directory over here, and you can see I just did it. It says 10 p.m. on my clock. It says it wrote this out at 9:59. And when I click it, voila! This simply tells me the row number, and I don't actually need this. I have my first digit, count, actual proportion, Benford proportion. We can widen this a little bit to see what we get. I'm going to go column width. We can set it all the way to 16, which is a nice number. And you can see we have an amazing level of accuracy over here. And all that you would do in Excel is to format this to a number and to the number of decimal places that we want. And indeed, we're almost at our goal of mimicking this. What you can see is that I have the mean absolute deviation in its own column on the right over here. There's a mean absolute deviation on the right. And basically, I'm almost good to go. So what I've done over here is to write the file to CSV. And now I'm going to move one step up. I'm actually going to get R to calculate the count. So let's go over here. It's going to do the group by. I'm actually going to get it to read the file called the digits. So this is the first digit of the first number, the first digit of the second number. We'll go all the way down, home and home, to the first digit of the last number. So we'll do Control Home. I'm going to import this, and I'm going to get R to calculate how many of each I have. Let me close the file so that I don't try to open it. Yeah, we can save this, I suppose, and we'll keep this format. So I'm going to go in here, read the file, and let's see what we get. Paste, and now we actually want to execute this. Run. And I'm just going to pause. I'm back. Hello again. Well, in my directory called R, I had this file, county pop digits, and I've renamed it from what it was. So here it is, county population digits. I have a heading here, FD for first digit, and I have the first digit of each number. You can get 5122. I'm just going to close this here, and the first digit here is 5122. So I have the first digits of my data. I went and I did a little adjustment here, and I used read table instead. File name, header equal true, which is put the FD at the top, separator equal comma. I only have one column, but this is pretty good. And it found county population digits without a problem. And what made this more beautiful than my previous code was I have the name of the file in green, and I have header equal true in blue, and this is sort of indirectly telling me I can find it, I can see it, I can see that file, it is there. I'm just going to run it again, run. And here you can see first digit counted as 3,142 observations, and there's only one variable, which is one column. So now we're going to get it to, so all I have is 3,142 of them, and I wanted to count. And the way we do this is we'd get the counts by going table. So we go back into R, paste, and I'm going to do table. Table means count. Count how many 1s, 2s, 3s, and count how many of everything I have. We'll do run, and let's see where it is. Ben test count. There we go. 953, 594, 374. Just remember that. Ben test count 953, 594, 374. The counts that we entered manually, 953, 594, 374. It got it. I'm just going to, we'll type it in here. No spelling mistakes, otherwise it'll come back. And I'm going to run, and there it is. R has calculated my counts. So, thank you to Brad Price. We are now at the situation where R can do pretty much everything here, except we have not got R to actually calculate the first digit. So if I go back here, File, Open, County, here we go. We have not got R to actually calculate that 5 is the first digit of 54571. That'll happen in part 2. Once R can do that, we should be able to then get the complete output in R, including having R calculate all these counts, including having R calculate the first digit and the counts. And then all you really need to do is to take my Excel file, and you can just plop this into Excel and it'll do the graph for you. Or we can actually see if we can get innovative, and we can actually get R to do a graph that looks just like our graph over here, if not better. So we can get R, if we know this, we can get Excel to do all of this and the graph, but what we want is we want R to do this and maybe the graph, and that'll be a project for the summer. So thank you very much. I hope you've enjoyed this. Please post comments or send me an email. I'd love to read them, and I'd even be curious to know why I went off track a little bit here with the set working directory and what little errors I might have made. So I'm going to post the files to Dropbox, and I'll post the links, and see you next time. Thanks for watching.